In 4.8 now we're going to do some more work in checking our model, and we're first going to review the assumptions that we're going to make. One is that we have quantitative data, so again that's numbers that you can measure. They have units, things like eye color, political preference, religion. Those are sorts of things you can't use this on because they're what we call qualitative data. Even if it has numbers behind it, it isn't necessarily quantitative, so be careful. Make sure you know that it has units can be measured. Linearity assumption, so when we plot these our data, our x and y data in a scatter plot, they should appear to be a straight line. If they start to look like curves, if they start to look like clusters or blobs of dots, we shouldn't do our regression testing. Outlier condition, so we saw an example of this in class. If I have a dot that's way off in no man's land, it can actually greatly affect our calculations. So what we should do is we should calculate our correlation coefficient in some of these values with the outlier and without the outlier and see how it affects the model. And then equal spread condition, that's what we're going to look at here in this section. We're going to check a residual plot for equal scatter of all x values. So we're going to expand on that here in a second. So first off, residuals. So we have residual, we're going to use the letter E for it. It's equal to our observed y or our actual y, so that's the data we get, minus our predicted y, so our y hat. We get that from our linear model. So the straight line that we fit to our dots produces y hat values, and so we're going to subtract those two. So the residuals can help us see if the model makes sense, and basically what we're looking for in a residual plot is no patterns. We don't want to see any discernible pattern, no curves or waves, or the dots get bigger as you go left to right, or farther apart as you go left to right, I should say. We basically want no shape at all, and we'll see this here in a second. So here's an example. Amazon book prices. So what we do is we take the predicted values for the book prices and the residuals. So again, 0 means that our prediction was the observed data is exactly the same as the prediction. Positive residuals mean that, so if we have 7.5 here, that means the observed price for the book was $7.50 larger than our prediction. So all these dots that line up with that were $7.50 pricier than we thought, so we underestimated. Minus signs down here, so negative 7.5 means the observed price was $7.50 less than the predicted price, so we overestimated the price, and that's kind of, we might be happy about that because, oh, it's cheaper than we thought, and all the dots here would line up with that. Okay, now this one we don't see any patterns, so the dots should be scattered around 0, some above, some below, and we shouldn't see any kind of curves, or we shouldn't see any straight lines. We shouldn't see these getting further away from 0 as we go from left to right, or vice versa. And so this would be considered a good residual plot, and we can be pretty satisfied with our linear model. We should think, oh yeah, the linear model probably makes sense for this problem. Now here's one where we have a model where we see a pattern. So hopefully you see there's this pattern here of like a parabola. So our residuals decrease and then they increase, and that's bad. So that's probably means there's some kind of lurking variable or some sort of connection between our data, and it's not truly something we should be doing a linear model on. So a residual plot where you see a pattern like this, you should look back at your data and really ask yourself if it's appropriate for a linear model. One of the things we're going to use as a quantitative factor to actually judge how good our residual plot is we will find a standard deviation of the residuals. So this is kind of just like standard deviation for x or y. It basically says how far away from 0 do these dots lie. So again, 0 is kind of the magic number for residual. That means our model is perfect. We predicted the price, or we predicted the y value exactly. So the smaller this standard deviation of residuals is, the better. So it means our dots are very close to a straight line. Our residual plot is all close to 0. And so we'll actually calculate this here in a second and see what it looks like. So here's another one, and so we would say, you know, let's see if there's any patterns. I don't see any curves or straight lines, but notice the residuals near the left-hand side are all pretty close to 0, and as I move left to right, the dots are getting further and further away from this 0 line. So this is called equal spread condition, and it doesn't look like these dots are spread equally as I go. So this is, again, probably should make us question our model and look back at our data, see if a linear model is appropriate. Okay, so that's it for the PowerPoint. Let's go to Excel and actually calculate this ourselves. So here we have our example, what we worked in class, capacity of a computer hard drive in terabytes and its corresponding price. And we did this first part in class. We found the mean of the capacity, the mean of the price, standard deviation of the capacity, standard deviation of price. We did our correlation table where we found the R value, the correlation coefficient between X and Y. It's very high, 0.993. It's positive, so we know the dot should go up and to the right. Then we use that to calculate B1, which is, so we're trying to find the line that will predict these prices. So we found B1 is just R times SY over SX, and that's $98. And we found B0, which is mean of Y minus B1 times mean of X, and that's $17. So this is the y-intercept for our line of best fit, and this is the slope. So this means at 0 terabytes capacity, we would still pay about $17. So about every hard drive needs about $17 worth of equipment. And then as you increase by a terabyte, you add $98. So 1 terabyte would be 17 plus that. 2 terabytes would be 17 plus 2 times 98, etc. And so the equation for our prediction y hat is 17.78 plus 98 times x, where x is just the capacity of the drive in terabytes. So let's make a column in our table for predicted prices. So we're going to use this equation, and we're going to use these x values over here. So I'm going to type equals, and I'm going to say we're always going to have 17.78, so I'm going to say we start with that, plus we have $98 times 0.09, the x value. So at 0.09 capacity, we would have predicted the price to be $26 when it's actually $23. Now I'm going to do something here so I can copy this equation. We want 17.78 to stay put, so I'm going to put a dollar sign in between the letter and the number there. And we want B19 to stay put, because we're always going to use these two values in our equation. So I'm going to put a dollar sign in between that. And I'm going to hit enter, and then I'm going to right click and copy this. Then I'm going to select all these, and I'm going to paste. And then it just applied that same equation to each of these capacities over here. And these are now all predicted prices. Let me put these more in a better format. Let me format these to, let's actually do currency, 2 decimal places. So now we have dollars. In fact, let me do the same thing for these numbers here. Okay. And so now we have prices and we can compare. So we would have predicted for 1 terabyte drive, we would have predicted $115. Its actual price is $98. So we can see our predictions are pretty close. Now to find the residual of each of these predictions, we're going to say equal to, well, residual is y, the actual value, minus the predicted. So we're just going to click the actual y minus the predicted y, enter, and so we can see that we were $3.61 over what it actually cost, so we overestimated. And let me just copy that and paste it down. And let me just center these quick. Okay, and so we overestimated by 3, underestimated by 1, underestimated by 4, underestimated by 3, overestimated by 17, etc. Okay, so there's our residuals. Now let's actually look at this residual plot. So first we can insert this plot and see again just how good our data is. So there's our data, and so there's our terabytes on the x-axis versus price on the y. Now let me actually hide this, and let's do one for the residual plot. So for this I need to select the residual. Actually, we need to select the predicted price, that's going to be our x value, and then we need to select the residual, which will be our y value, and we'll insert this as another scatter plot, and there it is. And so what we have is 0 here. Predicted price goes along the x-axis, and then residual on the y-axis. So again, 0 means our model predicted it perfectly, and we can kind of see here it looks like maybe equal spread condition isn't satisfied, doesn't it? Because these dots here are pretty close to 0, within plus or minus $10. This one's down to 20. This one's all the way up to almost 40, and this one's almost down to 30. So we see our dots are kind of growing as we move left to right. So there's a good chance for this one we might think that the equal spread condition is violated. And you can actually look at this. So that we were $34 off. That's pretty big for this problem, especially since we were closer for smaller terabyte drives. So we might ask ourselves, is there something that changes? You can notice when we're below 1 terabyte, we predict pretty well. Our residuals are small. Above 1 terabyte, they get quite a bit. Our residuals are quite a bit off. And if you know anything about computers, you know that we can always kind of buy things. So the lower storage space things are always cheaper, and then if you want to start buying this cutting edge stuff, the price really jumps. And I think that is going to have something to do with our model here. Now let's do one more thing. Let's find the standard deviation of residuals. So that's SE, and if we go back to the PowerPoint just to recall the equation, it's going to be, we have to take each residual squared, add them all up, divide by n minus 2, and take the square root of that. So let's first square all these e's. So let's make an e raised to the second column, and all that's going to be is equal to, select your residual, shift 6 for caret to the second power, enter, and we're just going to control C and control V that. Now those are the square roots of all the residuals, and you can see for the small ones it's a small number, $1, $8, but when we're off by a lot. This $34 residual turned into $1,200 when we squared it. Now the equation then says add up all these, so this sigma here means add up all those numbers. So I'm going to hit equal, SUM, sum, select all these numbers, parentheses, enter, and it's about $2,000. Then it says divide that number by n minus 2, where n minus 2 is the number of data points. So we have 1, 2, 3, 4, 5, 6, 7. So we're going to divide equal this number divided by 7 minus 2, enter. So that's about $415 now. Now we have to be a little careful. The units of this are actually dollars squared because we squared the dollars. So the units will work out in the end. Let me in fact make these unitless just because of that. We don't want to confuse you. We've squared the units, then we're going to unsquare the units so they go back to normal. So let's just make it numbers for now, and then I'll explain at the end what it is. So we summed them, we squared them, summed them all up, divided by n minus 2. Now we need to take the square root of it, and so we'll say equal to square root of this number, and that is actually a price number, and it's the standard deviation of the residuals. This is SE. And again, the smaller that number is, the better. It's kind of hard to tell if it's a good number or not. We would almost really need another example of these hard drives to see just how low it can get. Obviously 0 would be perfect because that means our model is exactly spot on. So the closer to 0 the better. And that should do it for 4.8.